Good afternoon, everyone. So, today let's start discussing on the group velocity and phase velocity. So once we are discussing that waves are propagating and all those cases, so here it is important that what should be the velocity of the wave once it is going. So that concept's actually coming in there, that is phase velocity and group velocity. But now the important point is that, so we are not discuss in this lecture completely what is phase velocity, what is group velocity. Just I will introduce it. After that, once we will do the energy transmission through that, there we will discuss it thoroughly, that what is the group, what is the phase, and we will do the full derivation and all those things. But just like for time being, because we are discussing the dispersion relationships and all those, so these concepts are important actually, so that I will just introduce that. So phase velocity is known as Vp and this is Vg. So Vp is written as, you can think, eta divided by mu. So mu is what? Wave number, and this is frequency. Or you can also think that this is omega divided by wave number. Wave number is kappa. So you think the unit is 1 by meter and this is 1 by second. So omega equal to 1 by second and kappa equal to 1 by meter. So the unit is coming something meter per second. So that's not, so that is giving you the velocity term. And what is the Vg? Vg actually del omega over del kappa. So that also has the unit meter per second, or whatever, like a velocity unit, length by time. This way that things will come. Okay. So now if you think that we have a dispersion relation, like for example, let's say for monoatomic case, we have the dispersion relationship, that is minus eta square plus 2 into 1 minus cos mu, that is equal to 0. That was my dispersion relationship for the monoatomic case. Agreed? Perfect. So if this is for the monoatomic case, can we calculate what is the phase velocity and what is the group velocity? So how it will be? So my target will be eta divided by mu. We have to write it in that form, that eta divided by mu. So let's try to do that way. Or I can simply say that eta will be 1 minus cos mu root. Okay. So eta by mu will be equal to one by mu root over of 2 into 1 minus cos mu. So if you think 2 into 1 minus cos mu can be written as sin square mu by 2. Sorry, that is 4 sin square mu by 2. Okay. Cos mu equal to, if you think, cos mu equal to 1 minus 2 sin square mu by 2. So it is this. Okay, so I can write it 1 by mu into 2 sin mu by 2. Okay, so that is 2 by mu and sin mu by 2. So that is my eta. So eta equal to 1 by 2 mu into sin mu by 2. That's eta. Sorry, that is eta by mu. So that is my Vp. So the phase velocity is becoming 2 by mu into sin mu by 2. And what is the group velocity? Group velocity Vg will be equal to, how? We can do it del mu, del eta over del mu. Okay, if we are doing it del eta over del mu, we can also write it eta equal to how much? So root over of 2 into this thing, that is that is 2 into sine mu by 2. So del eta by del mu will be how much? 2 into cos mu by 2 into half, so it will become cos mu by 2. That is mu by u, that is eta by mu, but I have to do it eta. Eta, if you think, eta is just only this. Got that? Agreed? Very good. So group velocity and phase velocity, we got that. So now if you see here how that thing happening, so if we are plotting it in terms of mu, then we have seen that once this is, we are plotting in terms of mu, we can see that okay, so suppose if we are plotting it real mu, imaginary mu, and it is, we are plotting it eta, just I reverse that full thing. So this was going like that, and then group velocity, it will be starting from, sorry, phase velocity will be starting from 1. I'll just draw it with the other color. The phase velocity will be starting from 1, and that phase velocity will go like this, and group velocity is starting from 0. So that one is my phase, this is group, and this is my dispersion. Okay, important point. Or you can think it also in the normal manner as well. Like if you are putting it eta, here it is mu, or group velocity Vp or Vg, whatever. So this is going up, mu. So phase will go down, 1, it will go down, group will drastically drop. Very important point. If you see, group velocity is reducing to 0. At the onset of band gap, your group velocity is becoming 0. That is very important point. But you see, phase velocity is still there. It's very important point that group velocity will become 0 at the onset of the band gap, and you can see it invariably in any cases. Whenever the band gap is starting, group velocity is becoming 0. But phase velocity will be something, and group velocity and phase velocity at the very low frequency will be same. Okay, we have not discussed what is group velocity, what is phase velocity, but just assume that like it is actually showing that if we are giving a sinusoidal type excitation, how fast that excitation will move, that is the phase velocity. And group velocity is if we are sending a packet of waves, how fast that packet will move. Now packet of waves and a single frequency wave has a fundamental difference, because packet of wave contains some frequency, means it's a little band it has, but just a sinusoidal wave is just a single wave, or monochromatic wave, it's just a has a single frequencies. So with a single frequency excitation, monochromatic excitation, we cannot find what is the group velocity. Not possible. Means if you run that simulation, it cannot give the group velocity, because it has no component of del omega by del kappa term. That del omega point is not there, it's a single value. From single value we cannot find del omega. So that's why a small packet or small variation of the omega is required. So once we are giving that, then we can able to see that variation in that. Okay. We will discuss that full thing once we do the energy transportation. There we will discuss that thing in thoroughly. But for the time being, just for understanding, you can think that this way the group velocity, phase velocity is coming. So this is the important point, that group and phase velocity are coming like this. Fantastic. Now, if we see in case of the phononic crystal or that diatomic chain, what was happening? In that case, if you see our dispersion relationship was like this. Okay. And now actually from this graph also you can able to calculate what is the group velocity and phase velocity, because this is the graph of mu versus eta. What is the group velocity? What is the phase velocity? Phase velocity is eta by mu. Simple, the slope of that graph you can able to, slope on the other side, you can able to calculate what is the group velocity and what is the phase velocity, and del mu over del eta over del mu give what is the group velocity. But remember one important point. If you are calculating directly from this graph, you have to understand, once we are reaching to the pi, next time this band we are showing here, but it should not be like this, it should be flipped. Means I'm just plotting only the real, so it is pi, so actually it is what, it is going up like this, then we have a gap, so gap is fine, then this thing is basically mirrored, should be mirrored from 2 pi. And you can see that is basically a fantastic scenario. You think that thing is going like normally if there was no change. If the mass remains same, that will go as it is. But as the mass get changed, it just snapped. So reality is it is going like that. But why we not plot it like this way? Because it saves the space. And you see that once we are calculating it, it is coming like cos of mu is something. So once we are calculating mu, cos inverse or mu or sine inverse something. So that's a general function. So it is always giving between 0 to pi. So that's why we are getting it 0 to pi, not in that upper side. But once we are trying to calculating the group velocity and phase velocity directly like this, we have to use the unfolded version of it, not the folded version. Folded, so this is known as the folded dispersion. What directly, like if you are writing a MATLAB code, you are using the cos inverse type function, so directly it is not going into the general formulation, it is just showing the value between 0 to pi, or maybe minus pi to pi. In that range it is giving you all the values, so you are getting it in that range. Done. We are not going the upper side, but in reality it is actually going higher and higher and higher. So once we are trying to calculating the group velocity and phase velocity, because here you see that slope is coming. Now if it is opposite way, your slope will be changed. The slope of these, like this point, let's say this point, slope is here. So you will completely misinterpret. Okay, got that idea? Clear? So in this case, how the group and phase velocity should look like? So phase velocity will be coming like with some value. It will come, it will go down, and then again it will have some value and it will go down. Like this way, that phase velocity will work. And group velocity will go like this. It will also start from the same value, but it will go 0. Again it will start with some value, and it will go to 0. Got that? So at the boundary, phase velocity again, group velocity again, you see, is becoming 0. But now the most interesting thing, and mostly you can say for which that full subject actually started, or that full concept of metamaterial actually exists. It is not only that it gives a band gap in that region, as well as some physics quantity also is coming into it. So how that is happening? So what is this? So once people try it for the mass in mass case, it is going up, then imaginary part is going down. Forget it, because imaginary part we are not bothered, because if you see imaginary part, why we are not bothered? Because imaginary part, wave is not at all propagating. So when wave is not propagating, there is no question that what is the speed of the wave. It is not propagating, man. So how it can have a speed? So that question itself nullifies. So we are not bothered, we will not going to calculate it in the imaginary part. That's the band gap. Wave is not going. But once the wave is going, we will try to see what is the phase velocity and group velocity. I think that makes sense also. So here you see that this is going like this. Okay, and then comes like that. So that is the folded part. So in the unfolded, how it should look like? Gap. Now this thing will come like this. Okay, so what's the problem? What's the problem? Is there any problem? Phase velocity will increase, decrease. It also has some value and like that. Okay, phase velocity is coming like that. What about group velocity? Zero. Makes sense. The most crazy thing, group velocity become negative. That means what? Exactly. That energy is moving in the opposite direction. And now I hope you understood that that is not just a simple TMD type phenomena, the tune mass damper or something like that people are putting inside the resonator and all those things, but it is not just only that. It has much more things behind. So most of the cases people are misunderstood that metamaterial type subjects that okay, it's just extension of the TMD. No dear, it's not that. It's not that because there we are not at all discussing with the speed of the wave, how the energy is actually transmitting and all those things. We are not at all discussing those things. So here you can see that this type of peculiar phenomena may occur. That's really very interesting. And here the group velocity becomes negative. So realization of those things, like suppose you have a chain and you just impacted it and you try to see that how the wave is propagating, and once it is coming like okay, where it is going, like you can see that wave is moving in the, like the velocity of the wave packet is in the opposite direction. That's a quite different thing. Okay, so with this I would like to stop today's lecture. We'll meet in the next session. Thank you very much.